Welcome to the ID Alliance G7 Master Basic Training Minimum Required On-Site Curriculum. It includes changes to the G7 Master Program, what is G7, what is Grackle, SWAP, and CGATS 21, what are the principles and benefits of G7, how G7 differs compared to TVI calibration, the basic methods of G7 calibration, how to use G7 with ICC profiles and why you would want to, some discussion about verification and tolerances of G7, and then G7 process control aims and tolerances. Looking at the G7 master changes effective as of 2015, the primary changes are mandatory on-site training, including this curriculum, a checklist, and an affidavit. These slides will be available as an online tutorial, and other support material will be provided. Another big change is that a G7 master must specify which compliance level they are aiming for. That could be G7 Grayscale, G7 Native CMY, G7 Targeted, or G7 Color Space. Why are we changing the program? To make it stronger and more valuable to G7 masters and to prospective clients who search the G7 master database. To ensure consistent operation of the G7 methodology, and to help distinguish market focus and capabilities of each individual G7 master. The new G7 Expert training begins as of the second quarter of 2015. Optional compliance with the new rules begins April 2015. Mandatory compliance begins April 2016. What is G7? G7 is a universal grayscale definition that controls the two visual parameters by which we judge the appearance of grays. These are gray tonality, in other words, lightness and contrast, and gray balance, or the neutrality of a gray area. What else is G7? It's a simple, fast, one-step calibration method that can be applied to any printing system, so long as it uses C, M, Y, and K inks. And the same calibration is used for any device, any inks, any substrate. So it's a universal system. The core G7 concept is that gray balance and gray tonality of any printing system can be controlled simply by adjusting the individual ink curves of that device. G7 standardizes this idea to produce a common shared neutral appearance across all printing systems. The best way to describe shared neutral appearance is with a picture like this. Along the top row, you see three different printing systems in their native state. On the left is a digital electrophotographic printer, in the middle is an inkjet printer, and on the right is an offset press. And this is how they looked when they were simply plugged in and switched on. Simply by applying G7 curves, but no other form of color management, we've produced the results you see on the bottom row. And you can see that they're very similar to each other, especially in the neutral areas. The gray tonality, or lightness and darkness, has now been normalized, and the gray balance is virtually identical between them all. But if you look at the golf ball, you'll see that actually G7 is not able to correct the color of the golf ball. The three of them, or three yellow balls, are different colors. This is because the ink colors on these devices were different. So you see that G7 is very good for correcting neutrality, but it doesn't necessarily affect the color of saturated parts of the image. This is because G7 is not an ICC color management system. The practical implications of G7 are that we will get the same brightness and contrast on all printing systems that are calibrated to G7. That means predictable gray balance and tonality, either with standard or non-standard inks and substrates. And it means we're going to get pleasing color, as we saw in the previous slide, even without ICC color management. But be aware that G7 is not a true color management system. As I said earlier, G7 only color manages grays. If you want full color management, for example, to correct the color of those yellow golf balls, you would require some ICC profile or color management on top of the G7 calibration. But other colors are actually improved when grays are controlled, and this is the basis of G7, and it's a 100-year-old secret of color photography. Color photography began in the late 1860s and was always controlled by putting some kind of a gray element in the picture. In color photography, gray has always been the control color. Here you see a grayscale that is frequently included alongside a subject when its reproduction has to be controlled throughout the whole printing process. And this process has been known of including a grayscale for over 100 years in color photography. Even today with digital cameras, gray balance is the key to getting good color. Here on the left you see an original digital photograph taken underwater with a very strong blue cast. Simply by applying red, green, and blue correction curves in Photoshop, we've restored colors that you can barely believe are in the original scene. No additional color management or hand manipulation was done. This is showing very clearly how getting the gray balance right and the gray tonality right actually goes a long way to restoring the original color of an image. Even though we don't necessarily know exactly what the color looked like, getting the grays right has taken us a long way towards a pleasing result. And this is one of the reasons why G7 has been so successful. Now let's talk about Grackle and Swap. Grackle is an ID Alliance specification defining the appearance of good commercial printing. Swap is an ID Alliance specification defining the appearance of good publication printing, for example in a magazine. These are precise definitions of how ideal printing should look. They are common targets for design, prepress, proofing, and output departments to aim for. A specification can also be known as a CRPC, or a Characterized Reference Print Condition, but please don't call them standards. The only organization that can issue printing standards is ISO, the International Standards Organization. Growing from the success of Grackle and Swap 2006, ID Alliance recently published a new set of 7 G7-based reference print conditions, which are registered with CGATS under the name CGATS 21. These reference print conditions cover a wide range of printing methods from newsprint to high-end commercial printing and beyond. What links them together is all have the same shared neutral appearance thanks to G7 and thanks to the use of similar hue angles for their primary inks and secondary overprints. Here you can actually see an absolute reproduction of the 7 CGATS 21 reference print conditions. On the left is cold set newsprint, next to it is heat set newsprint. Then we have uncoated, calendared uncoated paper, swap, which is the same as publication paper, Grackle, which is a commercial paper, and finally on the right we have a slightly expanded color set typical of some inkjet systems. What you're seeing here is the full appearance of these reference print conditions, including the color of the paper. And so you see that they look very different. But in the next slide, I'm going to show you what happens when we remove the paper color by doing a relative adaptation from the original color space into Adobe RGB. And here you can see what happens when we remove the paper color by doing what's called visual adaptation. So now we've actually represented here how each one of these printing systems would look if the human eye was only looking at that one at any one time without the others for reference. The human eye automatically adapts to the brightest area of a printed sample and subconsciously decides that that is white. This is very similar to the relative colorimetric rendering intent. And so you can see that simply using these reference print conditions, simply using G7 and standardized ink hues, we're getting a very, very good commonality between all these different types of printing system, at least in terms of gray balance and tonality. Obviously, if you look at the dark end on the left, we're printing on newsprint. It cannot hold very much ink, and so we have very weak shadow areas. But that's where the human visual system is most tolerant. The important thing is that the lighter tones, including the flesh tones, look very similar across the whole sweep of these 7 CRPCs. And this is largely due to the unique qualities of G7 being able to give this shared neutral appearance. The 7 new CGATS 21 CRPCs, as I said before, are newsprint cold set, newsprint heat set, high quality uncoated paper, publication super calendared paper without a coating, publication coated paper, which is also known today as Swap 2013, and commercial coated, which is known today as Grackle 2013, and then a generic large gamut color space. Okay, so this brings us to the subject of Grackle 2006 compared to Grackle 2013. There is a new version of Grackle, and a lot of people are very concerned about, oh my gosh, the sky is falling. Relax, relax, relax. It's a very slight change. In fact, most people cannot see the change unless they're using the absolute rendering intent. The reason these changes occurred is because in the last 10 years, optically brightened papers with OBAs or fluorescent brighteners have become more prevalent, and so the typical color of paper now is slightly bluer and slightly brighter. So we've published, or Idealliance has published, some characterization data sets that reflect that. But these differences are really only going to show if we reproduce them in an absolute rendering intent. For example, if you're making a proofing system using absolute rendering intent. There's also a very slight change in some of the solid ink colors based on 10 years of experience internationally as to how inks really do sit on top of each other in an offset printing situation. But again, I want to stress that the difference is smaller than the typical variation between the beginning and the end of a press run. And for many people, these differences are going to be insignificant visually. Bottom line, there's almost no difference. It's okay to use either Grackle 2006 or Grackle 2013 until such time as one of your customers says it's critical that you support the new specification. And to put that into perspective, here is an accurate representation of Grackle 2006 on the left and Grackle 2013 on the right. If you can't see a difference, it probably doesn't matter. Now let's go over some of the G7 principles. To understand G7, we first have to understand traditional calibration. And most calibration systems until G7 was invented were based on what is called TVI calibration. TVI stands for tone value increase, and it's just a new phrase for what we used to call dot gain. TVI calibration looks at the 4 individual inks separately and attempts to adjust the performance of the printing system so that the dot gain or tone value increase on each step follows a predictable path for each individual ink alone. So if we look at traditional TVI calibration, by applying curves individually to those inks, and these curves could be in a RIP, they could even be in Photoshop, we are attempting to meet the standard TVI curves enshrined in the ISO 12647-2 printing standard. And this worked for many years reasonably well. But when we came to produce the Grackle dataset 10 years ago, we discovered that using these TVI curves did not give us a sufficient control over the visual appearance, the photographic appearance of the final reproduction. Here, for example, is one of the weaknesses of calibrating to TVI. This is a 50% black patch. Both of these black patches have exactly the same dot gain. It's actually 20% dot gain, but you can see they're very different in terms of lightness. How is this possible? It's possible because, as you can see here, the bottom scale from which that patch was taken was printed to a much lower maximum density. This could, for example, be printing on tissue paper or very poor quality newsprint. The problem is that TVI is a ratio of reflectance. So if your maximum density goes down, all of the other tones must get lighter as well. The problem is the human visual system is tolerant of variations in the shadow much more readily than it is of variations in the light tones, or what we call the highlight range. So the reproduction on the bottom would actually look washed out and overexposed or too light. And this shows that TVI is not a direct indicator of appearance or photographic appearance. Furthermore, there's another problem with TVI. It doesn't control gray balance. In the ISO 12647-2 standard, it is intimated that if the cyan, magenta, and yellow plates have the same tone value increase or dot gain, then the system will be quote-unquote in balance. But this shows that that's not necessarily true. Both of these patches are made up of 50 cyan, 40 magenta, and 40 yellow, the standard ratio of percentages that are supposed to be gray in offset printing. You can see that the top patch is nicely neutral, but the bottom patch has a green color cast. How is this possible? It's possible because TVI doesn't control gray balance. Even though we are running the same solid density of cyan, magenta, and yellow, you can see in both these scales, the bottom scale has got a distinct green cast. What could have caused that? Well, ink trapping could have caused it, pH on an offset press, ink opacity, ink hue. There are many factors that can affect gray balance apart from TVI. So attempting to say that equal TVI guarantees gray balance is just false. So how is G7 different from the TVI calibration system? First of all, instead of using the 4 scales, we simply use 2 scales. One that is cyan, magenta, and yellow only, and one that is black only. By measuring the actual color and tonality of the CMY scale, and by measuring the tonality of the black scale, G7 calibration achieves consistent tonality and gray balance directly using the same rip curves that were used with traditional TVI calibration. So you can see that G7 defines two critical visual gray parameters: tonality, which we define in G7 as NPDC, or neutral print density curve, and gray balance, or the neutrality of the correct balance of cyan, magenta, and yellow percentages. So we're going to look at these two parameters separately. First, we're going to look at G7 tonality, which we call NPDC, which stands for neutral print density curve. The G7 NPDC curves can be expressed on a graph where the horizontal axis is the grayscale dot percentage that was printed, and the vertical axis is neutral density, which can be abbreviated to ND. And you'll see there's two graphs here. These are the graphs that resulted from our original Grackle tests done in 2005. The blue graph is for the black ink, and the red graph is what we measured for the CMY ink. And where did we actually get these graphs from? We got them by simply measuring the neutral density compared to the dot percentage of two scales printed on a variety of different press tests that were run very carefully to ISO standard solid ink values on ISO standard paper and ink. And this was done using CTP, or computer-to-plate systems, rather than film-based plate. So in 2005, we analyzed the natural tonality resulting on an offset press from making CTP plates, or computer-to-plate plates, rather than plates made through film. But the original work was done to support the Grackle project. Very quickly we discovered that other printing processes also wanted to use the G7 method. And so we had to come up with a formula that adapted these original curves to meet with the higher or lower maximum density or dynamic range of different printing systems. And you can see that these curves form the shape of a fan, and they're actually published in what's called the NPDC fan graph. You'll notice that on this fan graph, regardless of the maximum density, as we approach the lighter tones, the graphs become aligned with each other. So all G7 calibrated printers, regardless of their dynamic range or maximum density, have the same highlight contrast. And that's very important because that is the region of the visual space that the human eye is most critical of. Now let's look at G7 gray balance. The first thing we had to do when defining G7 gray balance was define what were the percentage values of cyan, magenta, and yellow that were meant to be gray. And it turns out that in 2005, when we did this research, there were no rules. So we asked around internationally, and we discovered that everyone agreed that we would be printing a neutral gray if we had a 50 cyan, 40 magenta, and 40 yellow. But the relationship was not linear. Rather than halving that to 25-20-20, we discovered that we actually needed 25 cyan, 19% magenta, 19% yellow, actually 18.8 if you want to be precise, to get a gray at a 25% region. Towards the shadow end, things were more arbitrary, so we ended up with a nice smooth curve that produced a gray at the 75 cyan with 66 magenta, 66 yellow. Those other numbers you see in there are the values that are in the P2P25 target, which is used for verifying G7 and in some cases for calibrating G7. So the second part of defining gray balance, having determined what the percentage values should be to make a neutral, the second part was, what does a neutral look like? Now, if we look at the standard ICC LAB diagram, a plan view of it, we know that where A star and B star cross in the middle, they are both 0. That is nominally a neutral. It could be a white or a gray or a black. So originally we said, why not just define the grayscale as having 0A and 0B? But it turns out that when we did that on a non-neutral paper, for example, in this case, a paper that has a slightly pinky blue cast, a slightly positive A star and negative B star value on the white paper, if we made all the other patches of the grayscale exactly 0 A star and B star, we didn't get a neutral looking result. And this is due to the human visual system's ability to adapt very quickly to the white point of whatever an image is printed on. In other words, the paper or the substrate. So we came up with a formula that gradually included that white point, but less and less towards the shadow end. And the formula is quite simple. For any patch on that grayscale, the wanted A star or B star is equal to the A star or B star of the substrate or the paper multiplied by the fraction of 1 minus the cyan percentage of that patch divided by 100. In other words, we're simply multiplying the A star and B star of the paper by the inverse fraction of the cyan percentage of the level of that grayscale. To understand this a little more clearly, let's actually work a couple of examples. On the 50% patch of a grayscale, the cyan value is 50 on the CMY grayscale. Let's say the A star was 2 and the B star was minus 6 on the paper. Let's look at that fraction again. 1 minus the fraction of 50 over 100. Well, 50 over 100 is a half, or 0.5. 1 minus a half is a half, or 0.5. And so the desired A star and B star on a properly calibrated G7 grayscale at the 50% point is going to be half of whatever the color is of paper. It's as simple as that. So a half times 2 A star is 1 A star, and a half times minus 6 B star is minus 3 B star. If we measure a patch that is the 50% patch of a CMY scale and we get approximately half the A and B of paper, then it meets the G7 requirements for gray balance. Looking at the 25% patch, that's closer to the white paper, so we actually want a little bit more of the white paper color to be included in the desired A star and B star. So here the fraction is 25% cyan divided by 100, that's 1/4. 1 minus a quarter is 3/4, or 0.75. So the 2 A star of paper multiplied by 0.75 is 1.5. The minus 6 B star multiplied by 0.75 is minus 4.5. You can see this is now a slightly stronger representation of the color of the paper. And finally, as we go towards the shadow end, the 75% patch of the 3-color grayscale, the fraction is 75 over 100, that's 3/4. 1 minus 3/4 is a quarter, or 0.25, so we only want a quarter, or 0.25, of the paper color. If the paper A star was 2, we only want a half. If the paper B star was minus 6, we only want 1.5 B star. And as we progress all the way to the shadow end, that final patch theoretically would have 0 A star and B star, regardless of the color of the paper. Now, depending on how you're viewing this, these slides may or may not work, but this is an attempt to show you the effect of G7 gray balance on substrates of very different colors. And hopefully you'll see that on the left, where we're printing on very blue paper with a minus 8 B star, although the picture obviously looks blue compared to the images to the right, the grays within that picture, hopefully the way you're viewing this, will look pretty much the same color as the paper. In other words, they won't look a strong color different from the background paper. In the middle, we have an almost neutral paper that has just a minus 2 B star, and you can see that the gray is actually, again, very similar to the color of the background of the paper. And on the right, we have a very warm paper, a very yellowish paper with a plus 8 B star. This would be indicative of, let's say, a very, very cheap recycled paper. Once again, the grays here have actually taken on a large part of the color of the paper, but in a uniform way according to the graph you saw earlier. And compared to the substrate or the background paper there, the grays look pretty neutral. Now, whether you see that exactly or not is going to depend very much on how these slides are reproduced or displayed, so there's no guarantee you'll see what I'm seeing here. And now we have a look at what would have happened if we had kept the formula for gray to be 0A and 0B regardless of the paper color. Hopefully you can now see that on the left, on the blue paper, the grays actually look yellowish, which is the opposite of blue. Actually, those grays aren't yellowish. On this slide, they are perfectly neutral. But as you look at that blue area, the eye tends to adapt, and when compared to the bluish paper, the grays actually look yellowish, the opposite of blue. Meanwhile, in the middle, we see barely any change because the paper is basically very close to neutral. And on the right, hopefully you'll now see that the grays look somewhat bluish because we're printing on yellowish paper. The reason they look blue is because they're actually perfectly neutral, but the human eye is being fooled. It's trying to say to itself, hey, the gray should look the same color as the paper, but it doesn't. What you're seeing actually is the fact of visual adaptation working in your own visual system as you look at this picture. So hopefully now you understand why the G7 gray balance formula is paper adaptive. Okay, now we understand the theory of G7. Let's look at how we can calibrate a printing device to G7. There are two options for G7 calibration. There is the free graph paper method and the automated software method. We're not going to go over the graph paper method here. We're simply going to talk about your automated options. Regardless of whether you use the graph paper method or the automated method, there are some steps that need to be followed in a logical order. The first one is to stabilize the system, and this is often the hardest thing to do. Having stabilized the printing system in order to make it repeatable, so you can come back and do the same thing twice in a row or 2 days in a row. Next, we make a sample print with no color management containing the calibration target. Then we measure the calibration target and we calculate the rip curves either by software or by the graph paper method. And then we make a second print through those new rip curves, again with no color management, and we check the results. Now, on an offset printing press, that is frequently all you need to do. But any other type of printing, for example, inkjet printing or digital printing, you will probably need to add a seventh step. And this is not technically part of G7 calibration, so I'm using a different font color here, but it's part of a normal setup for most printing systems. And that seventh step is to create an ICC profile. So let's look at calculating rip curves automatically. At the time this was recorded, there are 8 certified automated G7 software packages available. IDEalliance has certified all of these to build accurate G7 calibration curves. In alphabetical order, that is AL1 Print Standardizer X, Bodoni Press Sign 6, Colorgate Production Server, Fujifilm ColorPath Sync, Heidelberg Color Toolbox, Hutchcolor Chromix Curve 3, Konica Minolta Color Care, Mutoh G7 Calibrator. And again, as I said, IDEalliance has actually tested all of these and found them all to build satisfactory G7 calibration curves. Other calibration packages that claim they do G7 actually do it with ICC profiles, and that's not considered G7 calibration. Unless the software generates curves for the individual inks, IDEalliance doesn't recognize that as a G7 calibration software. What if your RIP does not allow the use of curves? Well, IDEalliance will accept a sample that has been simulated using color management. And the method there would be to calibrate the RIP by the manufacturer's method, create an accurate ICC profile of the calibrated printer, assign a G7-based profile to the image, for example, swap or Grackle, and then convert the image to the printer profile. When you measure the new print, it should confirm G7 compliance. And this brings us to the subject of working with G7 and color management together. Many people ask, why should I use G7 if I'm already able to use ICC profiles? And there are some very good answers to that question. First of all, yes, you can simulate G7 using color management alone without necessarily building the G7 calibration curves. But if you first do a G7 calibration, it's going to give you several advantages. First of all, it can potentially extend the life of a profile, because if the device drifts, all you have to do is a fairly quick G7 calibration to bring its gray performance back to the condition it was in when the profile was made. This means less need to reprofile the device. And reprofiling is not only slower and more expensive, but is potentially dangerous. Secondly, G7 can actually improve the quality of an ICC profile or the use of ICC profiles, because in some cases the profile itself has to do a lot of work just to undo a bad tonality or a bad gray balance situation. If the G7 calibration fixes tonality and gray balance, the profiling software and the limited number of patches in the profiling target can actually do a more precise job of fine-tuning the colored areas of an image. Finally, one of the classic problems in some printers is the inability to reproduce very fine highlight detail. And this will not typically be fixed by an ICC profile conversion, but it can be fixed if we use G7 first. And this is due to limits in the actual content of a typical characterization target, such as the IT8.7/4. And here you can see the problems I'm talking about. On the left is what some people might call a highlight stain, or an offset printer might call doubling in the highlights. In the middle is a normal reproduction, and on the right is a problem where very fine highlights have been lost. In each of these images, we've used ICC color management to reproduce the original CMYK file on these 3 devices. The problem is, in the sky area, when no percentage values are higher than 10%, we get 3 very different reproductions. That's because in the case of the left-hand image, the 2% and the 3% dots were printing more like 5 or 6% dots. But the profiling software didn't know that, because in the IT8.7/4 target, the first sample that's measured is white, and the next one is 10, and then 20, and then 30. Anything between 0 and 10 is interpolated and assumed to be a linear function of what was measured at the 10% patch. So the profile doesn't know that the 2% and the 3% patches are printing too heavy. On the right-hand side, we have an example of a proofing system that's based on dye sublimation, where the first 2 or 3% dots don't do anything. They print white paper. Once again, the profile measured the paper, it measured the 10% patch, and decided that everything between there would be a linear average of the 10%, but that was not true. So where it asked for a 2% dot, it actually got 0. Where it asked for a 3% dot, it actually got 1, and therefore we have this washed out, unpleasant look. If a P2P calibration is done precisely, we can actually correct the 2, the 4, the 6, the 8, the 10% values individually using curves before we print the profiling target. This means we can actually restore or correct the errors happening below 10% very precisely with a G7 calibration, so long as that printing process has a consistent problem. Now you can see that by doing that first and then building the ICC profile, we were able to actually cancel the highlight stain and restore the lost highlight detail in the left and the right image. Okay, having done a G7 calibration, how do we test a proof or a print for G7 accuracy? To test the accuracy of proofing system, we really need to look at two important but separate parameters. One is how good is the color reproduction. The second is how good is the gray reproduction, or the G7 calibration. Unfortunately, the IT8.7/4 target, which is very good for evaluating color, is not good for evaluating grays. So the only way to really test a G7 calibrated proofing system or printing system is to print both of these targets and evaluate them separately. So how do we evaluate the neutral print density curve of G7? That's done by analyzing column 4 and 5 of the P2P 25 target, or another scale that just includes the same values as column 4 and 5. ID Alliance doesn't mandate that you print a P2P 25. If you have a system that uses a different calibration method, then you can simply print column 4 and column 5, or a target you've made up that contains exactly those same percent values. The unit that we're going to measure is weighted delta L star. In other words, the difference in L star from what was printed compared to what was asked for. The weighting function I'll talk about in a minute. The central 23 patches of each one of these two scales, not the first patch or the last one, that's 0 and 100, but all the other patches, the average weighted delta L star must be 1.5 or less. The maximum weighted delta L star must be 3.0 or less. And preferably you want to see numbers around about half that level. So you notice that delta L star was actually tested on both scales. Column 4 is black only, column 5 is CMY. Gray balance is only tested on the CMY gray scale. That's because there's no way most printing systems can adjust the gray balance of the black ink. So only on column 5, we're looking at a unit called weighted delta CH. That used to be called weighted delta F star. The name was changed a couple of years ago. Again, the average weighted delta CH must be 1.5 or less. The maximum weighted delta CH must be 3.0 or less. But what is this weighting function we've been using? The weighting function is simply a multiplier that is applied to all the measurements of all of the steps of the grayscale before they are averaged and before we look for the maximum. And what it does is it reduces the significance of errors above 50%, where typically the eye or the visual system is more tolerant of errors, and also where most printing systems struggle more to produce consistent results. So if you look at this graph, you'll see that on the P2P target, every patch from 0 to 50, either the delta L star or the delta CH, is multiplied by a weighting function of 1. In other words, the error that was measured is preserved intact. But patches above 50% are multiplied by a factor that decreases slowly towards the end, so that the lowest patch at 100% only is left with 1/4 of its original error. So this is what we call the weighting function. And what this means is that we have a little bit more flexibility or tolerance for gray balance errors and tonality errors in the darker regions of a reproduction where the human eye is less sensitive and less critical. So having tested the NPDC and the gray balance of the G7 function, we now need to know on a proofing system or a printing system, how good is the color reproduction of blue skies, flesh tones, green grass, that kind of thing. And for that, we use the IT8.7/4 target. It's printed, it's measured, and the measured CLAB values are compared to the reference characterization data. For example, if you were looking at Grackle 2013, the data would be compared to CRP-C6. And there are a variety of software packages that will do that comparison. What are the tolerances we're looking for? The tolerances for different types of printing system vary depending on the expectations that are reasonable to apply to those systems. For example, a proofing system must have much tighter tolerances than a printing system. These tolerances are discussed in the G7 Master Pass-Fail document, which is available to G7 experts and on the ID Alliance website. This document is in a constant state of review, so the illustration you see here may not be the same as the one you download. So having tested a proofing or a printing system, which is something you do after you set the system up, what do we do in daily production? Well, for proofs, it's vital that we include on every proof an ISO 12647-7 control strip. If you don't include that on the proof, there's no way of knowing if that proof was correct or not. This control strip is free at idalliance.org. What you're seeing is the 2009 version. There is now a new 3-row strip that's measurable with the i1 Pro or the ISIS, and this is also available at ID Alliance. These strips can be measured and then compared. Most good proofing systems will actually recognize those strips, and you can load that proofing system with your tolerances. It'll measure it automatically and tell you if you've passed or failed. But just because you measure a proof correctly doesn't mean to say it's necessarily going to match a printed sheet. The only way to view a proof compared to a press sheet that is scientifically standardized is under D50 lighting, as defined by ISO 3664:2009. And remember, D50 is not the same as 5000 Kelvin. Two standards are very, very different. The only one that applies in the printing world is D50. If you do not have D50 lighting, you can have some serious problems. This is what a single proof can look like under different types of lighting. Notice that the white paper surrounding the proof is the same under each lighting system. We've used simple visual adaptation to show that the human eye will actually work under almost any lighting system to make a white paper look white. But if you look under supermarket lighting, this is actually the same type of bulb they put in the meat section of a supermarket. Notice that the flesh tones on this proof have gone very red, very saturated. In the middle, you see D50 lighting, where the flesh tones are correct. And on the right, you see a cool white fluorescent. That's a very cheap bulb that costs less than $2 at a place like Home Depot, and is typically used in office lighting. And you see the reds are very deficient. Now, this is the same physical proof. What you're looking at here is metamerism failure, and it can critically affect what seems to be the accuracy of a proof or a printed result. Obviously, if you look at printed results under non-standard lighting, you're in a completely uncontrolled environment. One of the basic subjects of G7 that needs to be known by every G7 master and expert is the G7 control aims, and they are HR, HC, and SC. The HC, HR, and SC numbers or points were taken from the original calibration scales or neutral print density curves derived when we were establishing the G7 tonality. And these are what we call the NPDC control metrics. They are simple, quick, easily read points that will tell us if a printing system is running too dark or too light. HC stands for highlight contrast. That's the range between the paper and the 25% point. HR is what we call the highlight range, or the range of density between paper and the 50% point. And SC is the shadow contrast, or the range of density between paper and the 75% point. You'll see that these are color-coded. On certain versions of the P2P target provided by ID Alliance, you'll actually see on column 4 and column 5, there are patches on each one that are color-coded by a line above and below it, either in green, magenta, or cyan. That makes it easy to find the 25, the 50, and the 75, or the HC, the HR, and the SC patch. Highlight range is the neutral density of the 50% patch when the paper density has been removed. In other words, when you've zeroed the densitometer on paper. And it allows us to take a quick check to make sure that we're not printing too dark or too light in our middle tones. And the values, which are pretty much standardized for most printing, are 0.54 for HRCMY and 0.50 for HRK. In other words, if you want to test a printed sheet or a proof, you can quickly measure the neutral density of the paper. Let's say it's 0.05. Add that value to these two numbers you see here, so the 0.54 would become 0.59, and then measure that middle gray patch. And if the 3-color CMY HR patch is 0.59, then it's reading exactly right. If the paper was 0.05, add that to 0.50 for the black, you'd have a target value of 0.55. Measure a black 50% patch on the print. If it reads 0.55, then that's correct. Now, the other way you could do that is you could zero the densitometer on the white paper, and then when you measured the HRCMY patch, you'd be looking for 0.54, and you'd be looking for 0.50 on the HRK patch. So there's two ways of doing it. But you see, it's just a really quick way of measuring the density of that neutral middle tone patch, which is the most critical patch in the whole tone scale for qualifying the performance of a previously calibrated G7 device. Having measured the 50% patch, if the system is well calibrated and recently calibrated, it's probable that the rest of the curve is going to be pretty good. But you can go and measure the highlight tone by measuring the HC-CMY patch, which is a 25 cyan, 19 magenta, 19 yellow. And here the value we're looking for is actually 0.25 when the instrument is zeroed on the paper. So it's an easy number to remember. The HCK is slightly lighter because that's what we measured back in 2005 when we did our testing. That value is 0.22. So to check the performance of your quarter tones or the highlight contrast, measuring the 25% black, if you've zeroed on the paper, you'd be looking for 0.22. Or if you'd measured the paper first and you measured a value of, let's say, 0.05, you'd add that to 0.22 and you'd be looking for 0.27. Now, the 3/4 tones, or the 75% region, can also be tested very quickly. If you are making a Grackle proof or printing to Grackle specifications, then it just so happens that the two numbers are 0.90. So if you've zeroed the densitometer on the paper, looking at the black density or the neutral density on both scales, we'd be looking for 0.90. But this is a variable, depending on your maximum density. You can see that with different amounts of maximum density, the actual target value for the SCK and the SCCMY might be lighter or darker than 0.90. That depends on what the maximum density is. You can read that from this graph here, and there's another graph that's given in the G7 Expert training that makes it easier to determine what the target value is. So remember that the highlight range and the shadow contrast patches may vary if you're printing to a very different maximum density, but the HC value, the 25% value, is actually a constant, same for all density ranges. So having looked at how we measure the effectiveness of your G7 calibration and a proofing system, let's now look at the G7 compliance levels. There are technically 5 G7 compliance levels: G7 Grayscale, G7 Targeted, G7 Color Space, G7 Native CMY, and G7 Extreme. G7 Grayscale is determined if your grayscale calibration measures with an average weighted delta CH of 1.5 or less, and a maximum weighted delta CH of 3.0 or less, and the same numbers for the average and the maximum weighted delta L star. Now, G7 Grayscale is a very flexible compliance level. It's not a very fussy one. You can get G7 Grayscale with non-standard inks. You can choose any inks you like. As long as your grayscale is right in terms of average and maximum gray balance and tonality, it's a pass for G7 Grayscale. But it doesn't really mean very much. It means your neutrals are going to look good, but we don't really know how the colored images will look. Now, for certain printing, this is better than nothing, and therefore we include it as the base level of G7 compliance. But for most printers, you want to go further than just G7 Grayscale. The next level is G7 Targeted. This includes all of the requirements of G7 Grayscale, but it also requires that the ink solids are matched to a defined specification, such as Grackle or Swap, or any of the CGATS 21 CRPCs, within the tolerance of approximately 5 delta E for the solids or 6 delta E for the 2-color overprints. A classic example of a G7 targeted system would be most G7 calibrated offset presses, where we've used standard inks run to standard C-Lab level. With G7 calibration and standard inks, you're going to get a good neutral match, good solid color match, obviously, because we've just measured them. And you're probably going to get a good color match in the image areas as well, like flesh tones and green grass. But do remember, this is going to depend to some extent on other variables like the 3-color ink trapping, emulsification, opacity, etc. In an offset press, you're likely to come very close to the target color space because Grackle and Swap were determined for offset printing. However, if you do G7 targeted on another type of printing, for example, electrophotographic or inkjet, it's possible that although you would pass the G7 targeted requirements, you may get a more extreme change in colored areas. And we're going to look at that later on. So G7 targeted is ideal. It's the perfect tolerance, or the perfect aim point rather, for offset printing. Now, the pinnacle of G7 compliance levels is G7 color space. Again, this begins with all the requirements of G7 grayscale calibration. Ink solids have to meet the defined specification the same way for G7 targeted. But now we also look at the IT874 target, the characterization target, with 1,617 patches. And here we're looking for, in a proofing case, some fairly tight tolerances. The substrate, or the white paper, must be less than or equal to 2 delta E. The average of all patches must be less than 2 delta E, and the average of the 95th percentile must be less than or equal to 6 delta E. For commercial printing, we relax those tolerances somewhat because it's very, very hard to achieve those levels on a high production printing system. So for commercial offset, the substrate can now go up to a 3 delta E, all patch average of 4 delta E, and the 95th percentile remains at 6 delta E. Now, if you look at the G7 master pass-fail document, you'll see that we actually have more precise definitions for other types of printing like flexo and screen. So it's not just one brush fits all or one size fits all. A good example of G7 color space would be a Grackle certified or Swap certified proofing system, and there are many commercial systems out there. You're going to get a very good neutral match, very good solid color match, and very good match within the image colors like flesh tones and green grass on a properly calibrated Grackle or Swap certified system. As of 2015, Idealines is introducing a new variation to the G7 compliance level called G7 Native CMY. And this addresses a problem that became obvious over the last few years in a limited number of types of printing system. The G7 Native CMY adapts to the problem that certain printing systems cannot actually get a neutral 300% point on the 3-color grayscale due to peculiarities of the inks that are used on that system. Classic example would be an electrophotographic printer. So what we've done is we've changed the rules for those rare cases where it's impossible to get close to neutral at 300% on the CMY scale. If you can't do that, then there's a new formula here that's applied that will actually adjust the target curve so that down to about 75%, we're still aiming for the same gray balance as G7. So the result is going to look fundamentally very similar. But as we approach the 300% point, the curves gracefully move away to aim now for the native gray balance of that 300 CMY patch. I want to stress that G7 Native CMY is only intended for devices where it's impossible to make the 300% patch neutral by mechanical or chemical means on the printer. And once again, classic example would be certain electrophotographic printers, or perhaps an inkjet printer or a screen printer or even an offset press that was using special inks for some particular reason, for example, to expand the color gamut. Do not use the G7 Native CMY compliance level if you're trying to set up an offset press to match recognized color space like Grackle or Swap. So if you're running an offset press, do try to neutralize the 300% CMY either by ink densities, water balance, or whatever. Don't use G7 Native CMY. Now we come to a slightly strange G7 compliance level, which really has no metrics to it, but was nevertheless quite popular with a lot of users. It's called G7 Extreme. This is what happens if you G7 calibrate a process that exceeds the gamut, that is the saturation, and the dynamic range, that's the maximum neutral density, of a high-quality color space like Grackle. Obviously, we have to do G7 grayscale calibration, but now we're implying that you're going to be using wider gamut inks than any of the defined specifications. What you're going to get is a good neutral match because you've done G7 calibration. but your solid colors may be noticeably more saturated and possibly a different hue than what would be expected in offset. Your images are also going to be more saturated, but often they will be pleasing enough to be used for what we call pleasing color. So the extended gamut strategy would be to calibrate your device using G7, and now we could call that G7 Extreme Calibration. And then on top of those curves, please do make a custom ICC profile on top of the G7 calibration. You're going to need that for one of the two optional ways of working. Now we have essentially a marketing option. You can say to your clients, I'm going to match Grackle, fine. I'll convert the original file from Grackle into my custom color space, relative, without black point compensation, let's say, and that will give you a reproduction that'll look very close to Grackle. But if the client says, no, just give me all the color you've got, I'm not really fussed about exact color matching, then you'll switch off color management and print with G7, but without ICC profiles. Typically, the files are going to gain more punch in solid color areas, but otherwise they will hopefully stay reasonably close to the original image and be acceptable under the quote-unquote pleasing color category. RGB files, you're going to convert them to the custom color space, or if someone wants to know how would that look like on a Grackle press, you convert first to Grackle and then to the custom profile. And here is an example of a typical extended gamut strategy using G7 Extreme. On the left you can see Grackle 2006, and on the right you can see what we call the G7 Extreme result. Hopefully you can see that the saturated colors have become much more appealing, and yet the middle tonality, the grays, and importantly the flesh tones are still acceptable. Whether you'll get a result that is acceptable on all types of subject really depends on the system you're working with. Some inkjet printers have so much saturation that if you use G7 Extreme, it may not be appropriate for flesh tone work, but it might be appropriate for technical work. It really is up to the individual user. So the benefits of G7 Extreme is that it maximizes the saturation of a CMYK file printed on your device without the need for ICC profiles. It basically does something that can't be done any other way. If someone says, print the CMYK file to the maximum saturation you have on your device, the only way to do it is by G7 without ICC color management. You gain the advantage of shared neutral appearance with other processes, so to a large extent, the image is going to have some commonality with, let's say, a Grackle proof. It'll just be more saturated. And it allows the marketing arm of your G7 Master client to offer two product lines: pleasing color with maximum gamut that doesn't necessarily match a reference print, or accurate color that matches a reference print but with more restricted gamut. Just remember that there are some limitations to G7 Extreme. Different devices will produce quite different results under the umbrella statement of G7 Extreme. It is not a defined color space, it's only a concept. G7 Extreme systems can be very, very different from each other. Well, we're almost at the end of these slides. Just want to finish up with a couple of logical warnings about managing expectations. Like anything, G7 is not perfect. It doesn't guarantee perfect color. Nothing does, unfortunately. Remember, G7 only strictly color manages grays, not colors. However, remember also it does bring colors closer to what we call pleasing results. We saw that in the golf ball. We saw that in the underwater picture. Remember, G7 does not compensate for inconsistent systems or materials. If you keep on changing the ink you put into your press, obviously G7 is not going to compensate for that. If your process is unstable, if you don't have proper process control, proper temperature control, G7 is not going to allow for that. G7 does not expand your color gamut, sadly enough. Putting G7 on a newspaper press doesn't suddenly make it look like a Grackle press. And of course, G7 is not going to accommodate bad printing. It's not going to compensate for sloppiness. Remember also that G7 focuses on one of the most critical visual parameters, and that is gray balance. Unfortunately, that's one of the things that is most likely to vary on many types of printing systems. So we're essentially focusing on one of the greatest instabilities of many printing methods. The trick is to measure and average more than one sample before calibrating or before making press adjustments. Because even on a good printing system, consecutive samples may actually jump around a little bit. You may get one sheet that's slightly bluish, the other one's neutral, the next one's slightly reddish. There are things that can cause that to happen on certain types of printing. So be careful before you overreact to a small sample. And remember also that good G7 calibration requires more than one press test. You typically will have to repeat that calibration 2 or 3 times over perhaps several days and average the result, and the same rule applies to profiling. That completes the G7 Master Basic Training Minimum Required On-Site Curriculum. On behalf of ID Alliance, thank you for watching.